All right, now we're recording. That week off probably messed us up. But today we're going to start with talking about uh, out of class project that you're going to do. Something we get pressure from the 4 year school saying students should be blah, blah, blah. Students should be working in groups in class. Students should be working in groups out of class. We're going to create a project. And way back when, there used to be blank, blank for dummies, and it was a textbook series that dumbed things down that was actually really cool and really popular back in the day. Well, we're going to cover a topic called Big O notation, and we're going to do it now because you're going to see how it ties into ComSci, how it's been tying into ComSci, and how this whole efficiency idea is going to work. Okay, so if I come over here, well, let's do this first. Let's go to. All right. Did the screen change to something that says Big O?
Yeah.
Yes. Okay. So I'm gonna have you do a project. It's gonna be a video. It can be however you want. When I first started this years ago, every one of them was a talking PowerPoint. So I'm going to hit play on your project and it's just going to roll. I'm going to sit and watch. I don't want to be clicking buttons and doing any of that. I don't like when people just read what's on the screen. That's almost like I can't read, you have to read it to me. You can have stuff on the screen, but don't read it. As the years have progressed, people have gotten more and more into making videos, and this would be an example of one. And you're going to explain to me, because I'm a dumb, about big O notation. Okay? And they went through and did a fantastic job. Now, it probably looks harder than what it is. I'm going to see if I can pull up another one here. I don't know what they use, but there's cool stuff out there. And like I said, I've had some as simple. Uh oh, I thought I stopped it. I've had some as simple as a PowerPoint, a rolling PowerPoint, not one I click, but one where you're talking and describing what big O notation is. So coming back to here, you're going to see a document. This document gives you some possible websites. I haven't checked them all out lately. Some of them are dead links, but some of them are there to help you get started. YouTube has lots and lots of stuff that can give you a pretty good idea of how to do something like this. This is a 50-point project, and give me 1 second. Big O, Big O review. I think this is it. No, that's the wrong. There we go. So the day you turn it in, April, whatever it is, I'm going to be grading it out of 40 points. This is where I'm going to get the 40 points. Okay, the presentation 15 are down here. The other 25 are from up above. And then you're going to do a peer review. And if people in your group all grade you as a zero, you get a zero for the project. Okay, so you can't just freeload and say, Austin, Sophia, and Isaiah, you're in my group, but I'm not going to do anything. And hopefully I can get 40 out of 50 because, I'll take credit for what you all turned in. So the first 40 points are going to be from this sheet. The other 10 points are going to be from a peer evaluation. we have this to start. No, that's not what I'm looking for. I still haven't found what I'm looking. This to start. Due date is April 16th. You see the groups. One group is, I love, for like the first 3 times I taught this class, I had 12 students. And I had groups of 4 and groups of 6 and groups of 3, and it just worked over and over and over. We have 11 students. So kind of close, but these are your groups. Today, when we go into do stuff in groups, I'm going to say room 1, Slim, Sophia, and Daniel, you are now in room 1. Room 2, room 3. You're going to know which room to join. And then you're going to be able to, after we're done working, talk to each other about how we're going to communicate. Let's meet back in a week. Let's da 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 da. Here's my email. We can use his Zoom other than Mondays because he doesn't use it if we all want to get together, or use my Zoom, or use something else, your Zoom. Okay? You got the idea of what's going on here. Don't be afraid to email questions to me. Okay, so today we're going to get into the programming, all of the coding of what this binary tree looks like. How does this binary tree work? And I'm giving you a bunch of files, and we're going to talk about those in just a little bit. But we're going to start out with giving you an assignment. And I need to stop sharing, and I need to go to this. And I'm going to say, build a binary search tree with the following 9, let's make it 10 numbers. Somebody give me another number. Good, 20. Build a binary search tree with those numbers. What? You don't know how to do that. Okay. I should pause the recording. Hi, Corinne. So we built our binary search tree with the numbers 10, 21 to the right, 11 to the right, to the left, 6 to the left, and so forth. So we have a nice tree, binary 0 or 1, left or right. It's going to help me to search through things. What I'm going to do now is put you in groups, and I want you to give me the pre-order, in order, and post-order traversals for this binary tree. I'm going to start. Here is the results of what I got. I had to make a quick note to myself. The left and the right never change. The pre-order, the node is first. In order, the node is second. Post, the node is third. So my pre-order is node left, right. Node, then I go to the left. Node, then I go to the left. Node, then I go to the left. 10, 6, 2, 1. Then I go back up. There is no right. Go back up. There is a right, which is 7. No left. No. Go back up. Now I start down the right. But again, it's node first, so it's 21. Then I go to the left. Node first, then I go to the left. There's no node, so I go back and go to the right. Node first, no left, go to the right. Node first, no left, go to the right. Node is 20. In order, left node, right. So yeah, that should give me my sorted list. 1, 2, 6, 7, 10, 11, 14, 18, 20, and 21. Pre-order is the left, then the right, then the node. I go to the left, I go to the left, I go to the left. There's 1. Then I go to the right, it's nothing there. So I get the node. There's 2. Then I go to the right, there is a 7. Nothing after that. So now I go back to the node. Now I have a 6. Now I go back to the node. And instead of doing the node, I go to the right. Once I get over here, I go left. There's no left, so I go right. There is no left, so I go right. There is no left, so I go right. 20. Then I go back to the node. 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 And then I go back to finally the last node. So I have a list that looks something like that. This came up recently. We've talked about pre-post. So here it is back again, just like I promised. Next thing that you should be good with is, boy, I went through all of this of how do I delete? Here's two types of deletes. The first one might be, how would I delete head? Oh boy, I don't know. What if I wanted to delete a node, in this case 7, and 7 only had one child? And then the videos went through as, oh boy, man, we got to go and who moves over to where, and if temp pointer's left value equals num, and da 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 equals 0, and how would I do all of that? So this matched this. Its left had something, its right was blank, so I had to move this down to here. If this side was blank and there was something here, I'd have to, what are all of the steps involved in deleting? So we have this new data type, binary search tree. We have all the functions that goes with it. Is it empty? Head points to null. Delete. When I get into delete, one of the things I have to know is to delete one child. What about deleting two children? I come down and I connect to the right, and then this right side's far left, wherever it is, has to connect back up to there. So wherever this ends, it would then connect over to the 3. So this guy would kind of slide up. Again, we're looking at a linked list representation of all this that's going on. But we're slowly getting better with prevs and next, lefts and rights. Then if you have more questions on that, it was covered in the video. Okay. Now, the programs. Share my entire screen. And if I go to the programs, I have some stuff going on here with, I didn't even load up int binary to the header file and the spec file, but I loaded some things up here. Here's a sort. What have we got going on inside of this sort? I'm working with an array. Oh boy. Before I move on with to look at the array representation and how all this works with arrays, you notice line 60 to 65. That's that nice swap that you learned about back in 161 with two reference variables and how I can just swap them. Looks like that's, I'm sorry, wrong class. This is wrong class. Ignore that. I don't know why I put that up there. Get out of here. But I did give you the files for this. The inserting, the display, the search, and remove. Then, if you wanted to load them up, you could take a look at them. I got ahead of myself. I was in the other class. Okay, so a complete tree. A complete tree. What was that? Well, there was an example in the NIOF book. This is when we started looking at the NIOF book. And a complete tree was one where everything was filled in left to right. Is this guy a complete tree? Well, the answer is no. Yes, yes, yes. 3 doesn't have a left child. So it's not complete. It would be filled in top to bottom, left to right. So maybe if this 9 was a 2 and connected here, it would be complete. Is it a balanced tree? Is it a balanced tree? A
No.
balanced tree was one where the left subtree minus the right subtree in all cases was -1, 0, or 1. So the height here is 2. The height here is 3. This was a -1. The height 0 minus 1, that's a -1. This is a 0. If I look over here, this is a 1 minus a 2. That's a 1. That's a 0. This is a positive 1. So this guy is called a balanced tree. -1, 0, and 1. Bunch of time spent on day 2 in there. The array representation for this guy, if I erase these out, what size array am I going to need for this? Well, when I fill the array, this is going into location 0. So, I don't know how big I need, but 5 is in location 0. 3 is in location 1. 8 is in location 2. What is in location 3? Nothing. It's empty. Location 4, 5, 6, 7, 8, 9, 10, 11, 12. 9 is going to be in location 13. Again, this was 0. This was 1. This was 2. 3 is over here, but there's nothing there. 4, 5, 6. This would have 7 and 8 coming off of it. 9 and 10, 11 and 12. This would be 13. Did I mess something up somewhere? 0, 1, 2, 3, 4, 5, 6. I think that's right, isn't it? Okay. So 4 would actually have 4. Again, this was the problem with arrays. All right, in the video, let's see how good you are. Where is a parent? So every node has one parent. 3's parent is at 5. 9's parent is at 12. And in order to find the parent, we needed a little bit of a formula. A mathematical formula. Remember what it was? So let's see. 3 and 4 both have a parent at location 1. 5 and 6, their parent is at 2. If I give you the number 3 and 4, give me a formula that both of them will get me to parent location 1. By the way, how many got the pre, post, and infix right? Part of it right. Big chunk of it right. Okay, thanks, Carl. What about children? 2 has children at 5 and 6. 6 has children at 13 and 14. So if I'm working with an array representation, I need to know how to get to a parent or how to get to a child if I'm inserting or deleting. But I need to know how to get to that location. So the parent of 3 and 4 was n minus 1, integer division 2. 3 minus 1 is 2, integer division 2 is 1. 4 minus 1 is 3, integer division gives me 1. 5 minus 1 is 4, integer division gives me 2. 6 minus 1 is 5, integer division gives me 2. How do I find the children? Two n plus 1, 2n plus 2. When you all watch the videos, do you take notes? I hope so. I'm a little concerned. The first test wasn't as good as I'd like it to be. And I'm wondering, all the information is there, just not being absorbed while you're watching the videos. Okay. So, I'm going to put you back in groups. Your groups have program for you to work on. And then, like I said, I want you to get ways that you're going to contact each other to do this project. And what I'm going to have you do is go to int binary tree and one, count the number of nodes. Add a new function to that. If you get that one done, how would you go about counting the leaves? If you get that function done, can you calculate tree height? Well, if I take a look at this one that's been used a couple of times, I have this binary tree, and it's interesting the coding to fill a binary tree. That's all in those files I gave you. And the first one was to count the number of nodes. How many nodes are there? 7. 7. So here's 7 nodes. What ideas would you have to try to figure out how many nodes there are? Well, I'm going to pause it. I want, and let's see what's going on. We have a main that inserts nodes 5, 8, 3, 12, and 9. We do a display in order. We remove 8, we remove 12, we do another display. So that was 21.4. Let's go to 21.1. It's just inserting a bunch of nodes. 21.2, inserting the nodes, doing all 3 display, in order, pre-order, and post-order. So they're the good ones that we need to take a look at. And if I go to the spec file, I see, ooh, interesting, insert, destroy, delete. There's my 3 traversals. Okay. Under my 3 traversals, inside of here, basically what I'm doing in line 40 is I'm calling display in order, and it's going to call display in order. All right. What's that mean? That means it's calling itself. That means we're going to deal with recursion. So when I come down here to find there's my deletions. Remember I said there's crazy stuff going on with deletion. This is a lot of code. Probably should have given it to you a little early so you could have looked at it, even though last week was spring break. But check out my line 54, my in order display. Notice how it goes left. Then when it hits a node, it displays it. And then when it goes, and then it goes right. That's a pile to wrap your head around. If you go down to display pre-order, we're doing the node first, displaying it. Then we go left, and then we go right. So this recursion is going to keep track of all that's going on. So for what I want you to work on, being able to count the nodes, I'm going to say, use this idea of recursion to help you count. Add 1, otherwise move to the left or to the right. And if it doesn't move left or right and you get bumped out, so what you need in order to count the nodes is going to be inside of this display pre-order concept of recursion. Now, again, if I go back to the specification file, you see void display pre-order. It calls display pre-order with a root. It's not easy. Most of it was in the videos. Questions? Questions? All right. So you know what I want you to mess around with? I want you to mess around with count the number of nodes. Count the number of leaves. What's a leaf?
Isn't it like the end of the tree?
Is
And
it
what
like
about it? Go ahead,
a
Sophia.
a node with like no children or like
Yes, the left and the right both equal null. The left and the right both equal null. Okay, so use those ideas.